Good morning, everybody. It is Sunday, December 17th. We are getting real close to Christmas, aren't we? I'm getting real close to being able to do something else with my life aside from this AP Calculus Free Response Question Advent Calendar. But I got to do this bright and early, just like every day, because I'm going to a football game today, Pats Chiefs. So that should be interesting. It's actually supposed to be a really warm day today as far as Decembers in Massachusetts go. It's going to be like high 40s. Should be good. All right, let's see if we can find the 17th compartment on our Advent Calendar box of chocolates. Ooh, there it is. 17. 17's a cool prime, you know. It's twin primes with 19, and I'm a big fan of twin primes. Really interesting twin prime conjecture. Check that out if you've never seen it. I'll put the AP Calculus Free Response Question that we're doing today on screen now. The twin prime conjecture is the conjecture that there are infinitely many twin primes. Twin primes are primes that are just 2 away, which, of course, after 2 and 3, the closest 2 primes could be is 2 away, because all primes after 2 are odd. So if you have some prime after 2, the number right next to it would be even, and thus not prime. Oh, God. Sorry. Okay. Today's calculus problem, we got a big table and we got to do some like minimum stuff. There's an integral involved, second derivative stuff. These table problems can be kind of tricky. You know, you really got to know your derivatives and how to apply them to solve problems, because with the tables, you're typically given like the bare minimum amount of information that you need. So you really got to know how to make use of it. Very soft chocolate. Beautiful box, isn't it? I feel like I've spent so much time with this box. All right. That was a good chocolate. Let's do the problem. This is free response question 5 from the 2014 AP Calc AB exam. Let's read it. The twice differentiable functions f and g are defined for all real numbers x. Values of f, f prime, g, and g prime for various values of x are given in the table above. So here we have a big table giving us some information about f, f prime, g, and g prime. We can see, for example, that the derivative of f evaluated at x equals -1 is 0. We also have some information about their signs on various intervals. We can see, for example, that g prime is positive between -1 and +1, which means that g is increasing on that interval. These sorts of table problems often involve a little bit more abstraction than usual. Really got to know your stuff. Let's read part A. Find the x-coordinate of each relative minimum of f on the interval from -2 to 3 and justify our answer. Now, if we're going to have a relative minimum on this interval, we're going to have to look at the critical points where the derivative is 0. We know the derivative isn't undefined anywhere in this interval because we're told that f and g are twice differentiable. So we can take the derivative. We got to see where's the derivative 0. And again, we're talking about f. Well, by looking at the table, we can see that the derivative is 0 when x is -1, and the derivative is 0 when x is +1. So how do we determine if these critical points are the locations of minimums or maximums or neither? Well, we have to think about the sign of the derivative. We see that the derivative goes from negative to the left of x equals -1 to still negative to the right of x equals -1. So the function is decreasing and decreasing, and then it flattens out a little, and then it continues decreasing. So this would not be the location then of a minimum or a maximum. Remember that we're looking for minimums. This would look something like this. The function's decreasing, flattens out, and then just keeps decreasing. On the other hand, this other critical point, to the left, the derivative is negative, the function is decreasing, and then to the right, the derivative is positive, the function starts increasing. So certainly at this critical point, where x is 1, we will have a relative minimum. F has a relative minimum at x equals positive 1, and that is the only one. So there's our answer. F has a relative minimum at x equals 1 because this is the only critical point where the derivative f prime changes from negative to positive. Let's move on then to part B. Explain why there must be a value c between negative 1 and positive 1 such that the second derivative of c, f double prime of c, equals 0. Now, we don't have information in our table about the second derivative, so we're not going to be able to use, say, the intermediate value theorem to say that the second derivative goes from negative to positive, so it must cross 0 at some point. We can't do that. But we do have information about the first derivative, f prime. We have some values of f prime. So what we're actually going to use is the mean value theorem. We know that f is twice differentiable, which means that its derivative, f prime, is also differentiable, and so it's also continuous. We can use the mean value theorem. Because we know that f prime is continuous on this closed interval, and also that it's differentiable, we can apply the mean value theorem to say that whatever the average rate of change of f prime is on this interval, its derivative, f double prime, must equal that average rate of change at some point on the interval. So what is the average rate of change of f prime on this interval? Well, what we have to do to find that is take f prime of the ending point on the interval, so f prime of 1, and then subtract f prime of the beginning point, negative 1. This tells us how much f prime changed on the interval, and then we have to divide by the interval length, which is 2, 1 minus negative 1. That's the interval length. That's going to tell us the average rate of change. Now, f prime of 1 and f prime of negative 1, we can check our table to see what those values are. F prime of 1, we know is, let's see, where is it? Right there. It is 0. And f prime of negative 1, we see, is also 0. Okay, so coming back down to our average rate of change calculation, we have 2 in the denominator, and in the numerator, we just have 0 minus 0. Of course, then this average rate of change is 0, just like we wanted, because remember, part B is to show that there's some value c where f double prime of c is 0. There must be, by the mean value theorem, some point c where this instantaneous rate of change equals the average rate of change. And there's our conclusion. By the mean value theorem, there has to be at least one value c on this interval where f double prime of c equals 0, because we see the average rate of change of f prime on this interval is 0, so there must be a point where the instantaneous rate of change of f prime, which is f double prime, is also 0. Moving on then to part C. The function h is defined by h of x equals the natural log of f of x. We want to find h prime of 3 and show the computations that lead to our answer. So this is just going to be a little bit of chain rule. Let's put part C over here. If h of x is ln of f of x, then let's just quickly find h prime. We have to use the chain rule, which begins with the derivative of the outside function. The outside function in this case is ln. The derivative of that is 1 over the input. We don't want to change the inside function, f of x, right? Leave that inside function alone. And then multiply by the derivative of the inside function. So in this case, that's f prime of x. That is h prime, which makes it fairly straightforward then to evaluate h prime of 3. H prime of 3 is going to be 1 over f of 3 multiplied by f prime of 3. Now, hopefully, all of these numbers are in our table. If we go up to the table, what is f of 3? F of 3, we see, is 7. That's over here. And the other value we needed was f prime of 3. And f prime of 3 is 1/2. So this calculation is simply 1 over f of 3, so 1 over 7, times f prime of 3, so times 1/2. So 1/7 times 1/2, which is 1/14. That's h prime of 3. Moving on to our final problem, part D. Evaluate the integral of f prime of g of x, g prime of x dx from -2 to 3. Now, if you don't really understand u substitution, this might look kind of intimidating. If you do understand u substitution well, this should look pretty trivial, because when you're trying to do a u substitution integral, what you're looking for is an inside function, like g of x, it's inside f prime in this case. You're looking for an inside function whose derivative is represented outside, like elsewhere in the integral. These are the sorts of situations where you want to use u substitution. In this one, we see ln x, and the derivative of ln x is this other thing, 1 over x. So this is a prime candidate for u substitution. This integral, we have sine of x squared. The derivative of x squared is 2x, which is just a multiple of 3x, which we see out here. Also a perfect candidate for u substitution. When you have an inside function and its derivative elsewhere in the integral, that's when you should be thinking u sub. And that's all this is. So here's the integral for part D rewritten. Let's proceed with the u substitution. We're going to let u, as usual, be the inside function, in this case g of x. And then we have that du equals g prime of x dx. And we see how nicely that substitution is going to work. What is this integral equal to then? Well, we have the integral of, let's worry about the bounds in a minute. This is the integral of f prime of g of x, but g of x is u, and g prime of x dx is du. So it's f prime of u du. Now, what about the bounds? Well, the bounds should be, let's see, u equals g of x. So if we're integrating with respect to u, the lower bound should be g of negative 2, and the upper bound should be g of positive 3. Before, it was x going from negative 2 to positive 3, but when x goes from negative 2 to positive 3, u goes from g of negative 2 to g of positive 3. So these are our bounds since we're rewriting this in terms of u. And we can evaluate these using the table. Let's go look at the table. G of negative 2 is, let's see, right here. G of negative 2 is negative 1. And g of positive 3 is right here. It's positive 1. So the lower bound is negative 1. The upper bound is positive 1. That works out pretty nicely. Here's our integral from negative 1 to positive 1, f prime of u du. And now the integral of f prime from negative 1 to 1 is just f of u evaluated from negative 1 to 1. The integral undoes the derivative. So this is going to equal f of 1 minus f of negative 1. And of course, we can consult the table to find these values. Going back to the table, f of 1 we see is 2 right there, and f of negative 1 is 8 right there. So this is going to be 2 minus 8. So with a little bit of u substitution, a little bit of fundamental theorem of calculus, we get the answer is negative 6. Pretty cool little u sub problem. And that completes our solution to free response question 5 from the 2014 AP Calc AB exam. Let me know in the comments if you have any questions. Be sure to check out the full AP Calculus free response question advent calendar playlist, link in the description and the pinned comment. And if you enjoy these calculus videos, please consider supporting Wrath of Math by joining as a channel member for exclusive videos, exclusive calculus content, all sorts of great stuff. Thanks for watching, and I'll see you tomorrow for another calculus free response question.